So as I told in the beginning, the rate of a reaction is very important. It is an integral part of research and chemical analysis nowadays. Okay, because the it's a powerful diagnosing tool. Because you know, in the human body, if anything happens, so we are going to do some screening test, so like some MRA and some other test, other diagnosing test we are undergo. But for the reaction, in order to know the state of a reaction, that means how much it is completed and how the whether the reaction is fast or slow, and what are the factor which is affecting on chemical reactions. So these are the things we can learn by studying these chemical kinetics. That means in chemical kinetics we are going to study the reaction with respect to time. That is, we are going to monitoring the reaction, we are going to observe the changes in the reaction. So that's why it is a powerful diagnosing tool. Okay, and by knowing its kinetics, so we can suppose the reaction is slow, suppose the reactant is not reacting properly, or suppose the reaction conditions is not favorable for that reaction. So if we come to know all the difficulties to carry out the reaction, at least we can develop a new method for to conduct the reaction to get a proper product, and we or else we can improve the procedure of that reaction. And so this is helpful in a large scale in the industries, in the manufacture of chemicals, including fertilizers, drugs, and household cleaning items. Especially in the field of medicine, in the field of drug discovery, the chemical kinetics is very important. Why? Because once a drug is injected to body, okay, so so then they are going to study how it is acting on body, or how much time it's going to take to produce its activity and all. And so we are going to learn, and we are going to monitor the action of drug, so by using urine and blood. Okay, that is, once if you are injecting or giving a drug to a body, okay, so every 5 minutes or every 30 minutes or every 1 hour, so we are continuously analyzing urine and blood. So there you will come to know whether the drug is reacting or not, or it is affecting it, it's producing its pharmaceutical effect or not. So these are the things we can learn. So we can learn in the branch that is called as pharmacokinetics. That is, there we are going to diagnose the reacting molecule, that is, diagnose the drug whether it is reacting in our body or not. So these are some importance of rate studies. Okay, so now I am going to discuss second order reactions. So in the second order, order of reactions. So order of reactions mainly explain the effect of concentration on rate of a reaction. Dear student, you know very well there are many factors which affects the rate of reaction, that is temperature, pressure, and so concentration. So here the order of a reaction deals only with the concentration. That is, if concentration varies, the reaction varies. For example, I think while doing a simple salt analysis, if you have done this experiment, that is, you are taking a pinch of calcium carbonate salt in a test tube. To that you are going to add dilute hydrochloric acid. At that the reaction, okay, as soon as you pour HCl, it will liberate carbon dioxide gas. That is, we are going to observe, we call as brisk effervescence. Okay, and if you use dilute, the it slowly emits carbon dioxide. But if you do the same reaction, so take test tube, add pinch of calcium carbonate powder, and to the add concentrated HCl. At that moment the carbon dioxide will bump in the solution. That is, the reaction is vigorous. So this is enough. That is, it depends on what the rate of reaction. There we observe that it depends on concentration of HCl, okay, as well as carbon calcium carbonate. That's why concentration is another important factor that is going to affect the rate of reaction. So in physical chemistry, in chemical kinetics, so we are going to derive a mathematical expression, that is how So how concentration exactly, okay, how much concentration exactly, okay, change the reactions, okay, how much takes it going to time for this concentration. That is the relationship between the variation of concentration with respect to time can be calculated with the help of equation that is called as integrated rate expression. Okay, so now before going to that, so let us see some examples of second order reaction. So in second order reaction, the rate, okay, as I told, the rate of a reaction is equal to, okay, according to law of mass action, the rate of a reaction is equal to concentration of a reactant. Let us consider if A is a reactant, A and B are the reactant, okay, so the rate of reaction is depends both on A and B. So that is A power 1 and B power 1. So it depends on both A and B. So this is a experimentally determined rate expression. That is, if so, that's why rate is defined as. So we are going to take some of the exponents, okay, power of concentration term. The power here, the power of concentration term is 2. So that's why it is second order reaction. That is, we are written this equation R is proportional to so concentration of A and concentration of B. Why we written? Because both concentration A and B play an important role here. So they are decide the rate of reaction. That's why I included both A and B. And if you add the power of two concentration term A B, you will get 2. So this is the mathematical expression in order to express the order of reaction. Here order n is the thing, but order of reaction n is equal to 2. That is, so K is equal to, suppose sometimes a concentration of one of the reactant, okay, so that doubles the reaction. At that moment also the rate of reaction is 2. Sometimes both the reactant are equally responsible in order to increase the rate of reaction. That is, both the reactant contribute same in order to increase rate of reaction. So that's why, so this is called as second order reaction. And some of the example of second order reaction is reaction between, okay, hydrogen and iodine. It gives 2 molecules of hydrogen iodide. And reaction between, okay, nitrogen dioxide and fluorine, it gives oxide fluoride, okay, so it gives a compound. And 2 hydrogen iodide, it gives hydrogen plus iodide. So this is the experimentally determined rate expression for these reactions. Now let us derive the expression. Here there are 2 cases are possible, because so here let us consider reaction A plus B gives product P. Sometimes what happens, the rate of reaction depends on initial concentration of reactant A and B. Here there are 2 possibilities. Sometimes the concentration of A is equal to B. At that moment the rate of the reaction is different. Sometimes the concentration of A is not equal to B. At that moment the reaction, the integrated rate expression is different. There are 2 cases. One is at the similar initial concentration of a reactant and different initial concentration of a reactant. Okay, so let us consider the first case in which the concentration of a reactant equal. So let us consider, so A, small a is the initial concentration of reactant A and B is the initial concentration. Okay, here the concentration of A and B are both are equal. That's why A is the initial concentration of reactant A as well as reactant B, and X is the amount of A and B reactant at time t. So at time t the concentration will be, see, you just look at the reaction. Okay, at t is equal to 0. That means before the reaction the concentration of A, okay, reactant A is 100% initial concentration A, and B also A, and the concentration of product is 0 at t is equal to 0. But at time t, if reaction is started, what happens? The concentration of A and B is decreases, and simultaneously the concentration of product increases. So let us consider, so X is the concentration of product. Okay, if X is the concentration of product, what is the concentration of remaining reactant? So A is the initial reactant minus product, it gives the concentration of reactant which is remains at time t, and here both the concentration are equal, that's why the concentration of B at time t, that means after 5 minutes, after 10 minutes, O is equal to initial concentration minus the concentration of product. Okay, now apply the law of mass action to this equation. So after applying law of mass action, okay, that is rate of a reaction. We know that rate is the thing but, so rate of a reaction is the thing but change in concentration of a product with respect to time, that is mathematically indicated as dx by dt. So this dx by dt is proportional to, okay, a minus x into a minus x, because a minus x is the concentration of A, and okay, A minus X is the concentration of B. Both the concentration are equal. That's why A minus X whole square. Then, so dx by dt is equal to, we are removing proportionality by introducing constant k. It gives A minus. So dx by dt is equal to k into A minus X whole square. So if you rearrange this equation, okay, to integrated form, so we are going to get dx divided by A minus X square is equal to k into dt. So now let us integrate this equation 1. Integrate this equation number 1. So you will get, so equation number 2. So that is integration of 1 by x square is equal to 1 by A minus x into 2 minus 1. So is equal to 1. So you will get 1 divided by A minus x is equal to integration of integration of k into dt is equal to kt plus integral constant k dash. Now we have to calculate this integral constant. So and now let us consider at t is equal to 0, so the product also 0, and substitute the value of equation, okay, of this t and x value in the equation 2. So at that moment, so the x value becomes 0 and t value also becomes 0. Then so k dash is equal to, then k dash is equal to, then k dash is equal to 1 by a. Then substitute this, the value of k dash in the above equation. So you will get 1 divided by a minus x is equal to kt plus 1 divided by a. Then if you rearrange this equation, then take kt to LHS and send a minus x in a right, okay, RHS, the right hand side, and after rearranging you are going to get kt is equal to 1 divided by a minus x minus 1 divided by a. If you further simplify this equation, you are going to get kt is equal to, okay, if you simplify by taking LCM, you are going to get this equation. Then again after simplification, you are going to get kt is equal to x divided by a into a minus x. Then keep rate constant at LHS, then k is equal to 1 divided by at, that is initial concentration and time, so into x divided by a minus x. So this is the integrated rate expression for second order reaction. K is equal to 1 divided by at into x minus x divided by a minus x. So this is the integrated rate expression for a reaction in which the concentration of A and B are equal. Okay, so now let us draw the graph of, so 1 by A versus time. So we will get straight line. We will get straight line. So this is the graph of second order reaction. So now see the second case in which the concentration of A and B are different. That is the initial concentration. For example, the initial concentration is 0.1, A is 0.1 molar, the B is 0.5 molar. So initial concentration is different. So in this case, so let us consider reaction A and B. So P is the product and the rate of reaction is equal to K into concentration of A and concentration of B. And so A is the initial concentration, small a is the initial concentration of reactant A, and small b mole per liter is the initial concentration of reactant B here, reactant B. So here X is the concentration of P, okay, that concentration of P, and A minus X. So this I am telling this after the reaction, that is, as I told in the beginning, at T is equal to 0, that is before reaction. What happened before reaction? So let us consider this is A and B. AB are the reactant and P is the product. So the constant at T is equal to 0. So maximum concentration, that is A, the concentration of reactant A is equal to small a, and the concentration of B is small b, and the concentration of P is 0 at T is equal, T never 0, but here we are considering T is equal to 0 because we are not started reaction. Okay, so at time T what happened? So the concentration of A is decreases, it is not equal to A, so instead of that, so it is somewhat less than A, so that is equal to A minus X. So X is the amount of A reduced, that is amount of A reduced or reacted or equal to amount of product formed. And similarly, the concentration of B after 5 minutes or 10 minutes or at any time is B minus X. That is, there are two different, okay, in this derivations we are going to deal with two different initial concentration. As a result, at the time T, so we are going to get A minus X is the concentration of reactant A remaining at time T, and B minus X is the concentration of reactant B at time T, and X is the amount of product formed. So now let us apply the law of mass action. Okay, so we know that, so the law of mass action, that is the rate of reaction is nothing but, so is equal to, okay, rate of formation of product with respect to time, okay, is proportional to the concentration of A. Here concentration of A at time T is A minus X, and concentration of B is B minus X, that is that we are taken here. That is, then we are going to remove this proportionality by introducing constant K. In some literature, instead of K, K2 is there. So K2 is a rate constant of second order reaction. But I am considering a K here. That is, rate of reaction is equal to dx by dt is equal to K into, so concentration of A and concentration of B, that is A minus X and B minus X at a time T. This is equation number 1. Then you simplify this equation. So in order to integrate, so then dx divided by A minus X, okay, into B minus X is equal to K into dt. Okay, this is equation number 2. Then, so we cannot integrate this form. So before going to integrate, so we have to simplify this equation. So little bit mathematical knowledge is needed to simplify this equation. So we can simplify this equation by using partial fraction. So after simplifying this equation by using partial fraction, so we are going to get new equation, that is, so this is the solution for this equation, that is 1 divided by A minus B is equal to 1 divided by B minus X minus 1 divided by A minus X into dx is equal to K into dt. So this is equation number 3. Then integrate this equation 3. So we are going to get, after integrating, so this is the equation number 3. So integration, this is a constant, so keep it this outside. So integration of 1 divided by B minus X minus 1 divided by A minus X into dx, and keep K is constant, and integration of dt. Then if we integrate, so that is we are keep this constant outside, and we are going to integration of dx by x. We know that integration of dx by x, integration of 1 by x, we can say integration of, we know the standard formula, integration of 1 by x into dx is equal to ln x. Ln x, this is a natural logarithm, and later we are going to convert it to a common logarithm. So this is ln x, okay, and here b minus x is there, that's why integration of 1 divided by b minus x is equal to ln b minus x. Again we have to differentiate this, then differentiation of b minus x is equal to 0 minus 1, that is minus 1, that's why it becomes minus ln b minus x. Plus similarly integration of 1 divided by a minus x is equal to ln Actually, this is here negative sign is there. Negative ln of a minus x, and you have to multiply the differentiate, okay, term of a minus x. If you differentiate, you are going to get minus 1. So minus into minus plus 1, that's why you have got, so plus ln a minus x is equal to k constant. So k integration of k, kt plus c, integration of dt is kt, dt integration of dx is x, that is integration of dt is t plus integral constant c. This is equation number 5. Now simplify this equation, that is, so this is log a minus log b form. Let us, okay, and then apply the loss of logarithm. So 1 divided by a minus b is equal to log of a, okay, minus log of b form. It becomes ln of a minus x divided by b minus x is equal to kt plus c. Dear student, now, so in order to find out the complete solution for this, we have to identify the integral, the value of integral constant, okay, that is c. So it can be calculated by taking by this at initial concentration. At initial concentration, a minus x becomes what? At t is at initial concentration, t is equal to 0 and a minus x is equal to a. Then apply these two value in the equation 6. What happened? So log of a by, okay, 1 divided by a minus b into ln of a minus x is equal to a and b minus x is equal to b into k into t. So k into 0, that is, it becomes 0. Then c is equal to, okay, so when we put this value, when t is equal to 0 and x is equal to 0, we are going to get 1 divided by a minus b into ln of a divided b is equal to c. So this is the integral constant value. Then substitute the value, okay, in the equations, okay, in this equation. If you substitute the value in the equation 6, that is, so okay, if you substitute the value in the equation 6, so you are going to get equation 8, that is 1 divided by a minus b into ln of a minus x divided by b minus x into kt plus, so c value, that is 1 divided by a minus b into ln of ab, okay, so a divided by b. Then again simplify this equation, that is, so take kt into LHS and so send this LHS term into RHS. After simplifying, you are going to get kt is equal to, and okay, 1 divided by a minus b. After say, okay, if you shift, for example, this to this, you will, okay, this becomes, okay, negative log, okay, ln a by b. And if you apply the loss of logarithm, okay, then you are going to get equation 10, okay, k is equal to 1 divided by t into a minus b into ln of a minus x into b divided by b minus x into a. So equation number 10. Again, if you simplify, that is, so ln is equal to 2.303 into log. So replace common logarithm of base 10. Okay, this is actually base e. So it becomes, the mathematically it equal to 2.303 into log. So k is equal to 2.303 divided by t into a minus b into log of b into a minus x divided by a into b minus x. So this is equation number. So this equation is called as integrated rate expression for a second order reaction when concentration of reactant A is not equal to reactant B. This is a different case. In the previous case, we discussed concentration of A and B are equal. At that moment, we got different equation. Now, the initial concentrations are different. So, if initial concentration are different, obviously it affects the rate of reaction, and we are going to get different integrated rate expression. So, this is the integrated rate expression. Then, if you draw the graph of, so this term, okay, 2.303 divided by a minus b, this, okay, into log of b into a minus x and a to b minus 6 after experimental data. By taking experimental data, okay, put this is in y-axis, and time because it is a dependent variable and it is independent, sorry, this is a independent variable and this is dependent variable. That's why we put in x-axis and this is in y-axis. If you write the slope, okay, we are going to get positive slope. Okay, this is the graphical representation of this curve. So thank you one and all for listening my classes. My dear students, if you have any doubts, so you can interact with me and you can put your questions on comment box. So thank you one and all. Thank you.